So let's begin with the next chapter. Next chapter is the properties of solids. Okay. So now let's talk about the properties of solids. So what are some types of bodies? Some bodies are rigid bodies. So this is an approximation, right? So what is rigid body? When you exert an external force, then there is no change in shape or size of the body. Okay, so till now we considered what? Only point sized object, and then we considered rigid bodies only. Okay, that is in rotational dynamics we considered that bodies are rigid. So now we'll also consider the changes in shapes and sizes of bodies. Okay, so rigid body means when you exert some force there is no change in shape or size of the body. Then next is when you exert some force in practical, okay, the shape or size of most of the bodies will change, right? So then some of them, they regain their original shape and size, they are known as elastic bodies, and some don't at all regain the original shape and size, they are called as plastic bodies. Okay, so elastic bodies are those, so after removal of the external force which is deforming that or them, okay, they regain their original shape and size. So those bodies are known as elastic bodies. So if bodies do not regain their original shape or size or both after removal of the external force, they are known as plastic bodies. Okay. So what are some examples of elastic bodies? Rubber is an elastic body, steel is an example of elastic body. So these are almost perfectly elastic. Why almost? Because there is nothing like perfectly elastic body. Okay. So then clay, wax, etc., they are almost perfectly plastic. Perfectly plastic means they don't at all regain their original shape or size. Okay, clay, wax, mud, etc., they are plastic. And everything, not everything means almost or most of the bodies, they are partially elastic, means up to some extent they regain their original shape and size, but they don't regain it completely. Okay, so these are types of bodies. Then the external force that changes shape or size of the body, or it changes both, it is known as deforming force because it changes form of the body. Okay, so it is known as deforming force, right? And then the deformation means change in the shape or size or both. Okay, so these are some definitions. Are these clear to everyone? Yes, no? Okay, all right. So now next is elasticity. So what is elasticity? It is the property of a body by virtue of which it regains its original shape and size. Okay, the property of body due to which it regains its original shape or size, right? Shape and size. Okay, so why bodies are elastic? What's the reason behind that? So now if you think of, for an example, suppose this is a rigid support and you tie some wire to that rigid support and you hang this mass. Okay, then what happens is, so now when there was no mass, no weight applied to the wire, then the atoms inside the wire, they maintain some fixed distance between them. Okay, so why do these atoms like to maintain fixed distance? Because atoms are made up of what? So if I zoom it, so this is, suppose, the nucleus of atom, and then there are electrons. So you can say this is an electron cloud, okay, that is surrounding the nucleus, right? So a nucleus which is positively charged, okay, and electrons which are negatively charged. Then if you think of another atom in the surrounding region, okay, near to this atom, then what will happen? What kind of forces will be there? So there will be positive positive repulsion between the nuclei, right? Negative repulsion between the electrons, then positive negative attraction between this nucleus and these electrons, and positive negative attraction between this nucleus and these electrons, right? So there are lots of forces. Okay, so atoms want to stay at such a distance from one another where the forces are balanced, okay, where there is no attraction, no repulsion, right? All these forces are balanced. So that distance is known as the equilibrium distance. Okay, this thing is clear. Let's call it A naught. Okay, and then there are forces between these atoms, means we can say there are bonds between the atoms. Okay, so these atoms, they form bonds with the surrounding atoms, you can say. Okay, so then atoms in solid maintain an equilibrium distance where the net force is equal to 0. Okay, so now suppose you stretch these atoms, that means you exert some external force, and because of that what will happen, the wire gets stretched. It means that the distance between atoms will increase. So when distance increases, the force between atoms becomes attractive, and when distance decreases, it becomes repulsive. Okay, so it is the bonds between atoms or the forces between atoms are just like springs. If you push them close, then what will happen? The spring gets compressed, so bond gets compressed, you can say. Okay, and then the force acts in such a way that it wants to restore the distance. Okay, so the force will be repulsive, right? If you pull them apart, that means distance will increase. So it's just like a spring. As spring is stretched, what happens? It tries to compress itself. Okay, so just like that, there will be an attractive force between the atoms. Okay, so this thing can be understood from potential energy versus position curve. This is not there in our syllabus, but let's very quickly see it. This is the curve. It looks like this. This is potential energy versus distance between atoms curve. Okay, so it looks something like this. Then we know that the force is equal to what? It is minus of du by dx. Okay, negative of potential gradient, right? Potential energy gradient. We learned this in last chapter also in gravitation, and we learned it in, of course, work, energy and power. So the relation between the potential energy and force, it is given like this. Okay, so force is equal to minus of du by dx. So see, now if you go on this side, what will happen? So this u versus x curve, it has a dip at this point, and at this point the graph is flat. That means if you draw a tangent to it, it is horizontal. Okay, it's parallel to x-axis. What does that mean? If tangent is horizontal, means du by dx is 0 at this point. So this point is the equilibrium distance, right? So distance corresponding to this point is equilibrium distance. Okay, then at this point the force is 0. If you increase the distance, then what happens? The curve here has a positive slope, right? Curve here has a positive slope, du by dx is positive, but then force is negative of du by dx, means the force will be negative, and negative means what? Negative means attractive force. Okay, so if you go beyond this point, the force will be attractive. Then if you decrease the distance, okay, below this a naught, then force will be repulsive, because the slope here is negative, and negative becomes positive. Positive force means what? Repulsive force. So is this thing clear to everyone? Yes, no? Right? Is there a doubt in this? This is clear, right? Okay, then there are some definitions. This is the smallest chapter. Okay, so there are some definitions, so let's see them. So first one is stress. So stress is the internal restoring force per unit area. Okay, internal restoring force generated in the wire, let's say, or any object per unit area. Okay, so longitudinal stress, longitudinal, whatever you call it, it is also called as tensile stress. Okay, So when the external force that you apply changes the length of an object, then the stress in that case is known as longitudinal stress. So what is that? So suppose you take this wire, okay, you apply this load to the wire. Load means you apply some weight to the wire, that is mg, right? Then mg is the force acting downwards. So under equilibrium, what will happen? The restoring force generated will be equal and opposite to that of mg, okay? So then the longitudinal stress will denote it by sigma. Sigma is equal to what? It is equal to force divided by area. So it is mg divided by a, okay? Mg is the force applied and a is the area of cross section, that is, it is pi r square for this wire, right? Area is pi r square. So this thing is clear, very simple, right? So this is stress. Stress is force divided by area. Then let's see next one, volume stress. So now suppose this is also called as bulk stress. So bulk or volume, so it depends, I mean bulk or volume, okay, it is related to the size of the object, right? So volume stress is related to size of the object, okay? Okay, so here volume stress, or it is also called as bulk stress. Bulk means the size, amount of substance, right? So then now how will the size change? To change the size only, not the shape, you need to apply a force perpendicular to this object, right? So object is circular, not circular, it is spherical. So then the force must be perpendicular to the surface area and it should act equally from all directions, okay? So such a force per unit area is called as what? It is called as pressure, okay? So here what we are doing is, suppose this is some spherical ball, okay, made up of any object, steel ball or rubber ball, etc. You dip it in this liquid, okay? Then this liquid exerts pressure from all sides. It exerts pressure from all sides, okay? What is pressure? It is perpendicular force per unit area, right? And this pressure is known as the bulk stress or the volume stress. This thing is clear? Yes, no? Okay, but what is stress? It's the internal restoring force per unit area. Whatever pressure you apply from outside, same amount of pressure will be generated inside too. So that restoring pressure per unit area is the volume stress or bulk stress, and it will be equal under the equilibrium. Okay, so this is definition of bulk stress or volume stress. It is just pressure. Let's see next one. Next one is tangential stress, or it is also called as shear stress. Tangential or shear stress. Now what is this? So suppose you consider this book, okay, you put your hand on the book, this is a thick book, and then you just slide your hand like this. So what will happen? Its shape changes from this to this, something like this, right? Yes, no? Okay, so its shape changes, okay? So this force is along the tangent to the area, right? Suppose you are exerting force on this top area, but you are exerting that force tangentially, okay? So the tangential stress, or it is also called as shear stress. Shear stress is tangential force per unit area, okay? It is just tangential force per unit area, right? So now suppose this is some block. So earlier it was cubical like this, then you exert some tangential force on the top surface, right? So then what happens, different layers, you can consider different layers of the substance. So different layers get pulled by a different distance. So this topmost layer, you can say the topmost layer, it gets pulled by a certain distance. The layer below that, it get pulled by a little bit lesser distance. Okay, the displacement of the layer below that would be lesser. If you consider the displacement of layer below that, it will be even lesser, and the layer at the bottom will have least displacement, so you can consider it to be fixed. Topmost layer will be displaced the most, and the layer at the bottom will be fixed. So this block, which was like this, it becomes like this. Okay, so its shape changes. So the stress which changes the shape of an object, it is called as shear stress. So for shear stress, you need which kind of a force? For changing the shape, which kind of force is needed? Tangential force is needed. Okay. Right, this thing is clear? Everyone, yes, no? Okay. And suppose this much is the displacement of the topmost layer. Topmost means what? It will not be topmost always. Okay. What does it mean? It means that the layer on which you are exerting a tangential force. Okay. The displacement of that one is x. Then now this is the bottom layer. So now if you take original edge to the displaced edge, the angle between them, it is shear angle, right? Okay, if you take face perpendicular to this force, so the original face and displaced face, there would be some angle between them, so it is known as the shear angle. Okay, so very simple, right? So this was strain, this was stress. Next, let us see strain. Okay, so in case of mental condition, the stress and strain is equal, right? Okay, so I am under a lot of stress or a lot of strain, it's equal, but in physics it's different. Okay, so let us see what is strain. Strain is the change in configuration, okay, or it is also written as change in dimension per unit original dimension. Okay, so change in configuration, or another definition is change in dimension. This is not division sign. Okay, let me write or to avoid any confusion. Change in dimension per unit original dimension. Now what is this dimension? So dimension means the length, okay, or size, right? These are the dimensions, okay, the volume, etc. So for longitudinal strain, now what is longitudinal or longitudinal strain? So then when you exert a force in such a way that length of an object changes, the stress is known as the longitudinal stress, and the strain is change in length per unit original length. Okay, so strain is denoted by this letter epsilon, the change in length divided by original length. Okay, then volume strain similarly is change in volume per unit original volume, and shear strain is shift in layer. Okay, shift in top layer, let's say, divided by its distance from the fixed layer. So shift in this layer, it is x divided by its distance from the fixed layer. Okay, it is x upon L. In terms of the shear angle, this is tan of the angle. Okay, opposite side divided by adjacent side. And when angle is very small, so we have learnt it that angle is very small, sine of theta is nearly equal to theta, it's nearly equal to tan of theta. Okay, when angle is very small, we can just say it is equal to theta. Tan theta is nearly equal to what? It is nearly equal to theta for small angle, small theta. Okay, so these are longitudinal strain, volume strain, shear strain, right? Okay, so this is clear. These are just definitions, right? Okay, so next let's see Hooke's law. Okay, what is Hooke's law? So Hooke's law says under the elastic limit, now we have not learned it what is the elastic limit, but we'll see. Under the elastic limit, stress is directly proportional to strain. Okay, under the elastic limit, the stress is directly proportional to strain. Now what is elastic limit? Roughly we can say till the time the body is elastic. And what does elasticity mean? The body can regain its original shape and size. Okay, shape or size or both, right? So if after removal of external force body can regain its original shape or size or both, okay, then we can say that body is under the elastic limit, right? Okay, good. So under the elastic limit, that means the force that you are applying, it is not as much, okay, means it is still under some limit, so that the body is still elastic, then the stress is directly proportional to strain. Okay, so this is Hooke's law. So it is given by Robert Hooke. Do you know Robert Hooke? He has worked in physics as well as bio also, I guess. Okay, anyways, so Robert Hooke has given this law, and it is very important law, because most of the physics is oscillations only. Oscillations means it's related with this force, spring force. Okay, so this force, right, under the elastic limit, stress is directly proportional to strain. So where does it come from? So if you think about a spring force, that means if you take a spring like this and you connect a block to it, okay, and other end of the spring is connected to a rigid support, then suppose you pull that block, then what will happen? The spring gets stretched, okay, and then what will happen? So when spring gets stretched, then a restoring force I'm sorry, when the spring gets stretched, then what happens? A restoring force is generated in the spring, right? So when you stretch it, when you pull the spring, okay, when you pull the spring, what happens? It wants to restore itself, okay. So when you pull the spring, it wants to restore itself, and therefore the force will be what? In opposite direction to that of displacement. So if you pull it, it wants to restore itself, that means it wants to get compressed, so, and come back to the original length. So if displacement is in this direction, the force will be in this direction, and if you compress it, then what will happen? It wants to get elongated, okay, right, and come back to original length. So if you compress it, that means displacement will be towards left, let's say. So the force, the spring force or the restoring force will be in opposite direction. So it is always opposite to that of the displacement, compression or expansion, right, or elongation. So it is always opposite, that's why there is this negative sign. And in magnitude, this force is proportional to the displacement. More is the displacement, more is the restoring force. So restoring force proportional to displacement, but acts in opposite direction. That's why the negative sign. So this F is equal to minus kx. Okay, this is the spring force, right? This thing is clear, everyone? Okay, good. Then if you divide this restoring force by area, you get stress, and it's proportional to the displacement, right? If we just take magnitude, it's proportional to displacement. If we divide right hand side by the original length, then what do you get? You get the strain. Okay, so basically this is the longitudinal strain, okay, but you get this formula that stress is directly proportional to strain, okay, and this is the Hooke's law, that under the elastic limit, stress is directly proportional to strain, and stress is proportional to strain. So if you want to remove this proportionality sign, put an equality sign, a constant will enter. That constant is called as modulus of elasticity of the material, okay. it is denoted by E. It's known as modulus of elasticity of the material. So what is modulus of elasticity? It is just stress divided by strain. Okay, take strain on other side. So E is just equal to what? Stress divided by strain. Right? It's very simple. Okay, this is clear. Good. Then corresponding to the three cases that we saw, okay, change in length, change in size, change in shape. Okay, there are three moduli of elasticity. So what are those three moduli of elasticity? First one is Young's modulus. Now what is Young's modulus? So modulus is what? Ratio of stress to strain. So Young's modulus is longitudinal stress to longitudinal strain. Okay, the ratio longitudinal stress divided by longitudinal strain. Okay, so I myself call it longitudinal sometimes, longitudinal sometimes. Okay, anyways, so longitudinal stress is what? Mg divided by area. Okay, the force, external force divided by area. Okay, and I am calling it external force, but it is restoring force actually, right? So under the elastic limit, this external force and restoring force would be equal. So mg is the external force, same amount of restoring force will be generated. So we can always write restoring force equal to what? Mg. Okay, always means what? Yeah, in most of the examples it will be under the elastic limit only. Okay, all right, so you have stress equal to mg divided by a, and then longitudinal strain is delta L is the change in length, L is the original length. So dividing by delta L by L is multiplied by its reciprocal. So that's why we are multiplying by L by delta L, L divided by delta L, right? So what do you get then? Y is the Young's modulus. Okay, Young's modulus is denoted by Y. Y is equal to mg capital L divided by A times small l, A times delta L, right? A times delta L or small l. Okay, so let's fix the notation as delta L. Okay, so what do we get? Y is equal to what? mgl divided by A times delta L. And what is A? So most of the times this area of cross section would be circular. Okay, so actually I haven't seen any problem in which these wires were like this. This is called as parallelepiped, I guess. Okay, or area of cross section is square or rectangular. I haven't seen any example. So we can almost all the times write mgl divided by pi r square times delta L. Okay, so this one is clear? Yes, no? It's very simple, right? Okay, good. Then let's see next one, the bulk modulus. Okay, now what is bulk modulus? Bulk means it's related to volume, it's related to size. So it is volume stress divided by volume strain, and that is what is volume stress? So volume stress is pressure. What is volume strain? It is change in volume per unit original volume. Okay, but then there is a negative sign between the two. Okay, negative sign between the two. That means if pressure is increased, what will happen to the volume? If pressure is increased, what will happen to the volume? Volume will decrease, right? That's why there is the negative sign. Okay, so volume stress is just pressure. Volume strain, you can say it's minus delta V by V, because pressure and change in volume would be opposite to each other. Okay, and then you can move this V in the numerator and you can write bulk modulus as minus P times V divided by delta V. Okay, minus P times V upon delta V. So this is bulk modulus. Okay, then next is shear modulus, or it is also called as modulus of rigidity. Why modulus of rigidity? Because what is a rigid body? So shape and size you cannot change, right? Rigid body is the body in which the molecules maintain fixed distance with respect to each other. So if you are changing the shape, then what does that mean? It means that body is not rigid. Okay, the distance between molecules will change. Okay, so that's why this is known as modulus of rigidity also. Shear modulus, okay, it is also known as modulus of rigidity. This thing is clear. Why rigidity? All right, good. So then it's denoted by letter G. Okay, bulk modulus is denoted by B, Young's modulus by Y, and modulus of rigidity by letter G. So it is just shear stress divided by shear strain. Okay, what is shear stress? Again, the parallel force, that means tangential force to the area divided by that area, and shear strain is x upon L, right? Shear shear strain is x upon L, or you can say in terms of theta it is tan of theta. Okay, so shear modulus is F upon A, and dividing by x by L is multiplied by its reciprocal, so L by x. Okay, and we know that tan theta is equal to x upon L, so you can just put tan theta in the denominator. These are two formulae for shear modulus: FL upon AX, okay, or F upon A tan theta. Okay, F divided by A tan theta, right? So these are just definitions. Okay, right. Then next is compressibility. Okay, compressibility of a substance. It is 1 upon bulk modulus. Another definition, it's 1 upon bulk modulus, right? Compressibility is denoted by K or sometimes kappa, right? Kappa. It is 1 upon bulk modulus. Okay, this thing is clear. Okay, so shouldn't be all theory. Let's discuss some problems. Okay, then we'll go back to the stress strain curve. All right, so let's see this one. Let a wire be suspended from the ceiling, the rigid support, and stretched by a weight W attached at its free end. The longitudinal stress at any point of cross-sectional area A of the wire is. Tell me. This is from NEET 2023. So you will get the idea about the longitudinal stress at any point. Why option C? Why should its own weight? Wire is suspended from ceiling and stretched by weight W attached at its free end. Okay, the longitudinal stress at any point, it will be W by A only. Okay, its own weight is not at all given. Is it given? Right, it will be W by A only. Why W by 2A? This is very simple. Let's see next one. Assertion: the stretching of a spring is determined by shear modulus of material of the spring. And reason: a coil spring of copper has more tensile strength than a steel spring of the same dimensions. Okay, so now see, the reason is incorrect. I will tell you. The steel is more elastic than the copper. Okay, we'll see why. Right, so tensile strength of the steel is more. Okay, strength of steel is more than that of copper. Okay, we'll see how. But the assertion, is it correct or not correct? The stretching of a spring is determined by shear modulus. Is it correct, not correct? You can stretch it. Yeah, it's correct, right? You can stretch it, means you can change its shape. Okay, so A is correct, B is incorrect. So that's why it should be option A is false. No, no, no. A is true, but R is false. So it should be option B, right? Okay, yes, no. In spring, no, no. Length does not change. Length remains as it is, right? Okay. So if you stretch it beyond certain limit, then the length will change. So first of all, you need to make it, you need to convert the spring to the wire first. Okay, and then if you keep on stretching, after that point, the length will change. Now suppose you stretch it, you make it very straight, right? That means you have converted spring to wire, and after that if you keep on stretching, then the longitudinal stretch will come into picture, right? This is clear. Okay, good. So it is option B. All right, next, shear stress is related to length, volume, shape, area. Which one? It's a very simple question, right? But they can ask questions like this. Okay, if they can ask question like this one, okay, they can ask anything. So this chapter itself is very simple, right? And most of the times there is one question based upon this one. Okay, so shear stress is related to shape. Let's see next one. The angle of shear is 30° for a cubical body, and the change in length is, so x is equal to 250 centimeters. Then the original length of the cube is, very simple. Tell me. So we know that this shear, the tan theta is equal to x upon L. So if you want L, L is just equal to what? X divided by tan of theta, right? So that is equal to, what is X? X is 250, right? Centimeters. So convert it to meters because options are in meters. Okay, 2.5 meters divided by tan of theta is tan of 30 degrees. So how much is that? 1 by root 3. Root 3 goes to the numerator. So 2.5 multiplied by root 3. Root 3 is 1.732. If you multiply these two, then what would be the answer? 1.7. Okay, 1.7 times 2 is 3.4. 3.4 plus half of 1.7 is how much? 0.85. 0.85. So that thing would be 4.25. 4.3. 4.3 is the answer, right? Okay, good. So it's option D. Let's see next one. A wire of length L, area of cross section A is hanging from a fixed support. The length of wire changes to L1 when mass M is suspended from its free end. The expression for Young's modulus is, tell me. Okay, tell me which one. Option D, right? Option D, no? See, original length is L, final length is L1. That means what is the change in length? Change in length is L minus L1. Okay, and then no problem. Okay, so y is equal to what? mgl divided by area into change in length. Change in length is L minus L1. Okay, so it is option D, very simple. right? Yes, Indusha, this is clear? Okay. All right, let's see next one. The bulk modulus of a spherical object is B. If it is subjected to uniform pressure P, then the fractional decrease in the radius is. Tell me. Okay. So see, while solving these kind of questions, we'll consider 3P by B. Okay. The bulk modulus is B, right? And if it is subjected to uniform pressure P, then we know what is bulk modulus. Bulk modulus is P divided by minus delta B or delta V by V. Okay. So you have delta V by V minus delta V by V, that is decrease in volume per unit original volume. It is P divided by B. Okay. And then volume is equal to, this is spherical object, 4 by 3 pi r cube. So it's directly proportional to r cube. Option C. Okay, let's see. 4 by 3 pi r cube. So then change in volume per unit original volume, remember the first chapter, it would be equal to what? 3 times of delta r by r. If we substitute that here, then what do we get? So delta V by V is 3 times of delta r by r. So 3 times of minus delta r by r is V by B. So we can take 3 on that side. So minus delta r upon r means decrease in radius per unit original radius is equal to P divided by 3B. That's the answer. Okay. So it is correct. Option C. Everyone said option C. That's correct. And then it is correct with sign 2. Okay. Even if there is minus P divided by 3B. So here you need to be very careful. Still the answer would be P divided by 3B, because you have decrease in radius per unit original radius is minus delta r upon r, right? So there can be a question like this. Okay, I mean I can change this option D to minus P divided by 3B. Still it will not be correct. Which one would be correct? This one is correct with sign 2. This is clear? Okay, good. So now let's understand stress strain curve. So you might have performed this experiment in your lab, right? So we know y is equals to stress divided by strain. So what is done basically? So you take a rigid support, then you tie a wire to it and you hang some weight. Okay, suppose a pan is hung from this wire, and then we put some weights in this pan. So as we put the weights, okay, weight of the pan, suppose it's negligible, right? Or you can count the weight of pan too. If it is substantial, you can count the weight of the pan too. Then you put some weights, okay, 1 kg, right? So you start with some grams actually in the actual experiment. Okay, so I mean 100 grams, 200 grams. Okay, then you increase it. Okay, so you keep on putting these weights, let's say 1 kg, 2 kg, 3 kg, 5 kg, so on and so forth, like that. So there would be a weight acting downwards. Because of that, there would be some restoring force generated in wire. So restoring force is just equal to the weight under the elastic limit. Okay, so restoring stress per unit area, restoring force per unit area is called as the stress, longitudinal stress. So then what you do is, again there is some scale over here. Okay, there would be a wire of fixed length and a scale would be attached to that. A vernier caliper is attached. Using that vernier caliper, what you do is you measure the change in length of the wire, right? The change in length per unit original length is strain. Okay, you plot stress on this axis, you plot strain on this axis. So this is called as stress strain curve. Very simple, right? So then what happens? You keep on plotting right? For fixed value, some value of stress, you get some value of strain, and you plot the curve. So how does the curve look like? The curve looks like this, okay? Then what are the various points in the curve? So see, initially this curve would be a straight line like this. So to increase the stress, the strain will increase. So it's a straight line graph between stress and strain. Okay, so that's what Hooke's law say. Under the elastic limit, stress is directly proportional to strain, or strain produced is directly proportional to the stress. Hooke's law. Okay, so now your wire is perfectly elastic. That means if you put on weights, the length of the wire will increase. If you remove the weights, then length of the wire would decrease. Okay, if you increase the weights, that means you increase the stress, length will increase. If you remove the weights, the length will decrease. Okay, very simple, right? And it will be directly proportional. Okay, so this is said to be elastic. The wire is, see, if you remove the weights, then what happens? Wire comes back to its original length, that means its original shape and size. So wire is elastic. Okay, so then wire will be elastic, okay, till this point A, till the point A. So point A is called as proportional limit. Okay, can you see that? Yes, proportional limit. That means up to the point A, stress and strain, they are directly proportional to each other. Okay, then still after that, if you increase the weights, that means stress is increased, strain will increase, but they are no longer directly proportional. So this graph is curved after that. Till that point, it's a straight line. Till proportional limit, it's a straight line. Then it curves like this, but still wire is perfectly elastic. That means if you remove the weights, it will regain its complete length. Complete length means it will regain its length completely. Okay, right? So wire is perfectly elastic till this point too. Okay, so this is called as elastic limit, or this is called as yield point. Okay, so what is yield point? If you increase the stress beyond that, the wire yields. Yields means it no longer remains that much elastic. Okay, so beyond the point B, if you increase the weights, length will increase. If you remove the weights, now certain deformation is left in the wire. Okay, it does not regain its original length completely, right? And then after that, if you still keep on increasing the weights, if you keep on increasing the stress, then you get some point C. So at point C and after that, the wire has plastic behavior. Now what does that mean? So a permanent deformation will be there. So even if you remove the weights, now wire does not come back to the original length. Okay, so see here, if you increase the weights, the wire will take the curve will be like this. If you remove the weights, then you go back along the same curve, okay, till this point C. Then after point C, you never come back along the same curve. Now if you remove the weights, you will get back this curve like this. Okay, so this much deformation is left in the wire. This is called as permanent set, or it is just called as set. Set means permanent deformation. Okay, so this much deformation will be left in the wire. Okay, so wire will never regain its original length, right? Okay, so now a body cannot regain its original shape and size. It is called as which kind of a body? Plastic body. So from this point onwards, we say that body shows plastic behavior. Okay, this thing is clear? Yes, no? Okay, good. Then after that, now see, till point A, actually till point C, you had to apply huge stress for small change in length, or for small strain you can say. Okay, up to the point A, huge stress was required for small change in length. Okay, after that the amount of stress required decreases. After the point C, see what happens at this point. This graph becomes almost flat. Okay, so what happens, the wire flows by itself under its own weight up to some extent. So at point C, that means at the plastic point where the wire begins to show plastic behavior, what happens, the graph, so tangent to the graph would be parallel to strain axis. So wire flows under its own weight, okay, up to some extent. And then again, now also, okay, it will flow up to some extent means it will, length will increase up to some extent. After that you need to exert some weight, okay, you need to exert some stress, but now stress to be exerted, it's no longer nowhere close to this thing. Okay, it's nowhere close to the earlier stress required, okay, for same change in length. So then wire shows plastic behavior, means it does not regain its original shape and size. Okay, that means length here. Okay, so from this point C to the point D, at point D again what happens, see, you can see at point D what happens again, the graph becomes flat. That means if you draw a tangent over here, it will be parallel to the strain axis. Okay, so from point C to point D, now what is point D, I will tell you. So wire shows plastic behavior. Okay, and at point D what happens, now length of wire is increasing and increasing. That means wire is becoming weaker and weaker. At point D a neck will be formed. Okay, so that you can say it's a neck point, right? At point D what will happen, the neck will be formed. So this is the point corresponding to what, the maximum stress, okay, that wire can handle. So it is also known as, the stress corresponding to point D is known as breaking stress. Okay, breaking stress. So once the neck is formed, neck means a neck like this, right? A neck like this is formed in the wire. So wire becomes weak at certain point. Okay, then even after even if you remove the weights after that, the wire is going to break. Okay, even if you remove the weights after that, that means even if you decrease the stress, the wire will fracture once the neck is formed. Okay, so point is known as fracture point. So you remove the weights and still now wire is flowing, okay, and it would break, but it breaks at this point. So this point is known as fracture point. So is this curve clear, everyone? Right? Okay, good. So then after that, see, now you see the point D and E. If point D and E are very close, then this material is brittle. That means neck is formed, material breaks. Okay, neck is formed, wire breaks, so material is brittle. Okay, and if D and E are separated by a large distance, material is ductile. Okay, ductile means you can make very thin wires of that material, right? If D and E are separated by a very large distance, then the wire is ductile. You need to remember this. D and E, that means a point corresponding to neck point. Okay, the point at which neck is formed, the point corresponding to breaking stress, and the fracture point. Okay, if they are very close, that means the wire is brittle, and if there is huge separation, large separation between these 2 points, then the wire is ductile. Okay, this thing is clear, everyone? Right? So this is our stress strain curve. After that, let's see, uh, next thing is another definition, it is the Poisson's ratio. Okay, next definition is Poisson's ratio. This is Poisson's ratio. Okay, there is double S over there. This is not Poisson's ratio. Okay, so what is Poisson's ratio? It's the ratio of lateral strain to the longitudinal strain. Now what is this? So suppose you pull a wire, okay, you apply some weight to the wire, its length will increase. So if length increases, what will happen to the cross sectional area? The cross sectional area will decrease, right? If you increase the length, so suppose there is no change in volume of the wire, then if length is increased, that means you are increasing, you're pulling this material this way. Okay, so its dimension is increasing in this way. So what will happen to its cross sectional area? Its cross sectional area will decrease. Okay, so the change in diameter per unit original diameter, it is known as lateral strain. Change in diameter per unit original diameter, it is known as lateral strain of the wire. Okay, in the wire, right? And now why negative sign is there? A negative sign is there because when length is increased, what will happen to the diameter? Diameter will decrease, and that's why Poisson's ratio is minus delta d by d. This is change in diameter per unit original diameter divided by delta L by L. Okay, very simple definition, right? Okay, good. After that, next let us talk about the elastic potential energy. Now what is elastic potential energy? So when you stretch a wire or when you deform a material, an elastic material, and you remove an external force, what happens? So you know that there is a restoring force, okay, which wants to restore the shape and size or both of the body. Okay, now to restore the shape and size, see, when you displace it, okay, when you elongate a wire, you need a force, you need some energy, right? Okay, to restore it back also you need some energy. So what happens is you do some work against the elastic force. Okay, so that work gets stored as potential energy of the wire, which it uses to restore its length or its shape and size back. Okay, so that energy is known as elastic potential energy. So work done against the elastic force, right, it is known as the elastic potential energy. Okay, so to increase the length, some work needs to be done against the internal restoring force, okay, or elastic force you can say. It is called as internal restoring force. So that work gets stored as the potential energy of this wire. Okay, right? So not just this wire, if you increase the volume of something or you decrease the volume, still you are doing some work against the internal restoring force. Okay, against internal pressure in that case you can say, right? This thing is clear? Okay, good. So now suppose this is our wire, and as usual for small extension, suppose dl is the small extension, the work done against the internal force, restoring force, is F dot dl. Then suppose L is some intermediate extension. Okay, so dw is work done for small extension, it is equal to F dot dl. Okay, and now suppose initially of course the length of wire is L. Okay, and then you are changing it from L to delta L, but in between you have extension L, small l. Then how can you write the Young's modulus? Young's modulus can be written as y is equal to F upon A multiplied by capital L divided by small l, right? So small l is what? It is an extension. Okay, so the force can be written as, move these things on other side, F is equal to YAL divided by capital L, right? This thing is clear to everyone? okay, internal restoring force is YAL divided by capital L. Okay, so it tells you that this force is proportional to what? The extension. Okay, this is just Hooke's law, right? So you put that here. So what would be the work done, small work done? So dW is F dot dl. So that is equal to YAL divided by capital L multiplied by dl. Okay, so dW is the work done, which is YAL divided by capital L times dl. Okay, and work done when the length of the wire increases by amount delta L. Delta L is the final increment, okay, in the length of wire. So work done would be just integration of this thing from initial increment is 0, okay, and final increment is delta L. So integration of this thing, then y is constant, a is constant, L is constant. Y, L is the original length, right? L is original length. L is, we are taking L outside, doesn't mean that length is constant. L is the original length of wire. Okay, so that's why we are taking YA divided by L outside. Okay, then integration of LDL from 0 to delta L. This is very simple. Integration of LDL, it is just L square by 2. Then put the lower and upper limit. So lower limit is 0, upper limit is delta L. Right, put those limits. Then what do we get? So substituting that, we get YA upon L times delta L square divided by 2. And again, what we do here, okay, this is the work done. Again, what we do here is, you can write this half, okay, times YA upon L, and one of the delta L I am writing with this YA upon L. So what is this thing? YA divided by L multiplied by extension. Okay, so this is the force at that point. See, YA upon L multiplied by extension, this is the force at a particular point. Okay, so this is force at that time when extension is delta L, right? So then this is force and this is the extension, and that's why you get work done is equal to what? Half of force times extension. Okay, is this thing clear, everyone? Okay, it is equal to half of force times extension. Right, very good. Okay, so then work done can be written as half of load multiplied by extension. Okay, so this work gets stored as elastic potential energy, as we discussed at the beginning of this derivation. So the elastic potential energy of the wire, it is just equal to half of load multiplied by extension. Okay, and then if you want elastic potential energy per unit volume, so divide that by volume. So volume is equal to area multiplied by length, and that's why this U is equal to half of F into delta L. You divide that by volume, that is, you divide force by area, delta L by L. This thing can be written as what? Force upon area is stress, delta L divided by L is strain. So elastic potential energy per unit volume denoted by small u, it is half of stress multiplied by strain. Okay, U is equal to half of stress multiplied by strain. Okay, then you have Y is equal to stress divided by strain. Y is equal to what? Stress upon strain, and therefore U can be written as what? Half of Y multiplied by strain square. This thing is clear? Stress can be written as, here stress can be written as Y multiplied by strain. So just substitute that. Stress is Y times strain. So Y times strain into strain means Y multiplied by strain square. This is another formula. And then you can substitute strain is equal to stress upon Y, right? Strain, you move on this side, it is equal to stress upon Y. If you substitute that, you get U is equal to half of stress square divided by Y. Okay, this is another formula. So the elastic potential energy per unit volume has got these three formulae. Actually, it's only one formula, but you can substitute stress is equal to y times strain and you get this one. Okay, and strain is equal to stress upon y and you get this one. Right, it's very simple. Okay, this thing is clear, everyone? All right, good. And then after that, there is this final topic, that is thermal strain. So now what is thermal strain? So see, suppose you have a wire and temperature of the surrounding increases, then we know that substances expand when temperature increases, right? So length of wire will increase if there is increment in temperature. Okay, so then delta T is suppose rise in the temperature and delta L is change in the length of wire. What we can say about this change in length? This change in length would be directly proportional to the change in temperature. Okay, change in length would be directly proportional to the original length, right? And change in length, why? Because if original length is suppose 100 meters, change in length is 1 centimeter, original length is 200 meters, change in length would be obviously 2 centimeters, right? Yes, no? This thing is clear. Okay, so then you can combine this with this. So what do you get? Delta L is proportional to L delta T. Okay, delta L is proportional to L delta T, and then you remove the proportionality sign, put an equality sign, a constant will enter. This constant is known as the coefficient of thermal expansion. Okay, this coefficient of thermal expansion, or this is also called as coefficient of linear expansion. Okay, actually it is thermal coefficient of linear expansion. All right, so let me just write linear here. Okay, so this is thermal coefficient of linear expansion. Okay, that's denoted by alpha. So we'll see this in this chapter. We'll see this in thermal properties of matter also. This coefficient will enter there also. Okay, all right, then so this is delta L. If you divide that by the original length, okay, that means just move original length on other side, you get delta L upon L. So you just get alpha delta T, and this is thermal strain, right? It is not caused by anything else. Just because of the increment in temperature, the length is changed. So thermal strain is what? Change in length per unit original length, but this change in length is because of temperature. So this thermal strain is equal to what? Alpha delta T, right? It is just equal to alpha delta T. Okay, and then we know that stress is equal to y multiplied by strain. Stress is equal to y multiplied by strain. So therefore the thermal stress can be written as y multiplied by alpha delta T. Okay, thermal stress is just y multiplied by thermal strain. So thermal strain is alpha delta T. So thermal stress can be written as y multiplied by alpha delta T. This thing is clear, everyone? So let us see next problem. Two wires are made of same material and have the same volume. Okay, they are made of same material, they have same volume. The first wire has cross-sectional area A, second wire has cross-sectional area 3A. If the length of first wire is increased by delta L on applying force F, how much force is needed to stretch the second wire by the same amount? Okay, so this is the problem. Tell me. So volume of two wires is equal. Okay, so what we can say is V1 is equal to V2. That means L1 A1 equals to L2 A2, right? And then what would be L1? So L1 is given, no, the area is given. So area of first wire is A and second wire's area of cross section is 3A. Okay. So from here you get L1 by L2, L1 by L2 equals to A2 by A1, right? L1 by L2 equals to A2 by A1. You get this. And then now the length of first wire is increased by delta L. Okay, length of first wire is increased by delta L, and you want same increment in the second wire also. Okay, so with what force should you pull that second wire? Should you stretch that second wire? This is the question. So you have this formula, y is equal to what? F by A, okay, multiplied by L divided by delta L, right? You have this formula, yes, no? Okay. So Young's modulus is force upon area multiplied by length divided by change in length. Okay. So you can move delta L on that side, and therefore you get delta L is equal to what? Delta L is equal to FL upon AY. Okay. FL divided by AY. So delta L1 is equal to delta L2. This is given. Okay. So F1 L1 upon A1Y is equal to F2 L2 divided by A2Y, and you can just move this F2 on this side, or let's keep F2 as it is. Okay, y gets cancelled, and what do we get? What is A2? So A2 is 3 times of A1, right? A2 is equal to 3 times of A1, that's given. Okay, so I can cancel out A2. So A2 would be equal to what? 3 times of A1. So I get 3 here, and then you have L1 equals to what? L1 is to L2 is A2 is to A1. So you get 3 here. Okay, or shall we take it on same side so as to avoid the confusion? Okay, so F1 would be equal to what? It is F2 multiplied by this thing, L2 divided by L1, okay, multiplied by A1 by A2, right? So F2 multiplied by, so L1 by L2 is equal to what? A2 by A1. So again what you can do is, in place of L1 by L2 you can put A2 by A1, means L2 by L1 is equal to A1 by A2. So you have A1 by A2 square, A1 by A2 square, right? And then what is A2? A2 is 3 times of A1, so this is 1 by 3 square, that means 1 by 9. Okay, so you get F2 by 9 is equal to F1, or F2 is equal to, so this is 1 by 9 times F2, that means F2 is equal to what? 9 times of F1. Okay, this is clear? Yes, no? Let's see next one. The problems would be similar. So see this one. The Young's modulus of steel is twice that of brass. Okay, 2 wires of same length and same area of cross section, one of steel and another of brass, are suspended from same roof. Okay, same roof, and they have same length, same area of cross section. So let's say length of steel is equal to length of brass. Okay, area of cross section of steel is equal to area of cross section of brass. What else? If we want the lower ends of wires to be at same level, then the weights to be added to the steel and brass wires must be in the ratio of. So again, you want lower ends at the same level, means delta L in steel is also equal to delta L in the brass. Okay, length is equal, and you want, they are suspended from the same level, and you want their lower ends at the same level, means change in length is also equal, right? Then what is the question? Then the weights added to the steel and brass wire must be in the ratio of. So you have, again let's take the same formula, y is equal to what? FL divided by F upon A times L divided by delta L. Okay, then you want same change in length, so delta L is equal to, take F times L upon AY Okay, so delta L in steel, this is again comparison kind of question, is equal to delta L in brass. So force in steel, force applied to the steel wire, okay, times length of the steel wire divided by area of cross section of steel wire, okay, Y of steel is equal to force uh, applied to the brass wire times length of the brass wire divided by area of cross section of brass wire, Young's modulus of brass wire, okay, brass wire, right. So what is same? L is same, okay, so L cancelled out. Then what else is same? Area is same, okay, change in length is same, we have written down that condition, okay. And then what is given about the Young's modulus of steel is that of, it is twice that of brass, okay. So Young's modulus of steel is 2 times that of brass, okay. So if we cut this, we'll get 2 here, we can move that 2 on other side. So force applied to the steel is equal to what? 2 times of force applied to the brass, okay. And we want ratio of force applied to steel, that means weight applied to the steel, to that of the brass. So Fs by Fb would be equal to what? 1:2, right. Oh, Fs by Fb is 2:1, sorry, I said 1:2, 2:1, right, it's option D. This is clear. Let's see next one. The approximate depth of ocean is 2700 meters, okay, some ocean, approximate depth, okay, in some ocean at some place is 2700 meters, right, because depth of ocean is also different at different locations, okay. The compressibility of water is 45.4 multiplied by 10 raised to minus 11, okay, per unit Pascal. That means it is compressibility is what? It is reciprocal of the bulk modulus, okay, and density of water is 10 raised to 3 kg per meter cube. Then what fractional compression of water will be obtained at the bottom of the ocean? This is the question. Okay, tell me. So this is also simple, right? So we know that bulk modulus is equal to P divided by delta V by V, right? Pressure divided by delta V by V, and you want delta V by V, so you can move it on other side, okay. It will be minus delta V by V, because if you increase the pressure, what will happen? Volume will decrease. So minus delta V by V is equal to P by B, okay, pressure divided by bulk modulus. But what is 1 upon bulk modulus? It's compressibility. So you can say it is equal to P times of K. K is compressibility, right? So then is the pressure given? Pressure is not given, right? But what's given? The depth of ocean is given. Then density of water is given, okay. Actually we should remember density of water is 10 raised to 3 kg per meter cube, 1000 kg per meter cube, okay. And with respect to that, all other densities are found, right, relative densities are found. So this number is something that we should remember, okay, because sometimes they might not give it, okay. So then compressibility is given. So how to find out pressure? Do you know? How do we find pressure? Okay, so let me tell you the formula. Formula is rho g h, right? Pressure due to the liquid, okay, at depth d, it is equal to rho g times d. D is the depth, or you can say pressure due to liquid column of height h is equal to rho g h, okay. So this thing actually it's there in the next chapter, but we can take it as a common sense, okay. So pressure is equal to rho g h. Just put it over there. It is rho g h times k. Okay. Now just put the values. So fractional change in volume, that is delta V by V, is equal to what? rho g h, so rho is 10 raised to 3, g is 10, okay, h is 2700, right, and then k is 45.4 multiplied by 10 raised to minus 11, okay. So what's the answer? So that is equal to this 10 times 10 raised to 3 is 10 raised to 4, 10 raised to 4, and this is 10 raised to minus 11 means minus 7, okay. Then you have 2700, so that will be 10 raised to minus 7 plus these two, okay. So 10 raised to minus 5, 45.4. So it is 1.2 multiplied by 10 raised to minus 2, right? So option A, no issues, okay. So problem is simple, right? Okay, good. Let's see next one. Copper of fixed volume V is drawn into wire of length L. When this wire is subjected to a constant force capital F, the extension produced in the wire is delta L. Which of the following graphs is a straight line? Okay, tell me. Copper of fixed volume V. Volume is fixed, so volume is constant, right? It is drawn into wire of length L. Then wire is subjected to a constant force. Force is a constant. The extension produced in the wire is delta L. Which of the following graphs is a straight line? This is the question. Okay. So again, we can write down formula for extension. Extension is FL upon AY, right? Extension is FL upon force into length divided by A multiplied by Young's modulus. And what is constant? Force is constant, volume is constant. So force is there, so we can take it as constant. Y is constant because it's Young's modulus, it is constant, right? So y is constant, but A is not constant. So what we can do is we can adjust volume over there. Okay, we can do some adjustment. So let's multiply and divide by L. Okay, so what do we get? So force is there, y is there, area times length is volume, and in numerator there was already one L. Again you have multiplied the denominator by L, so you need to multiply numerator also by L. Okay, so this area times length becomes volume, and that is a constant. So all these things are constant, and you have L square, right? You have force divided by y multiplied by volume. This is all constant, okay, because area into length is volume, okay, and volume is given to be a constant. So this is all constant, and then you have L square, and therefore you can say delta L is directly proportional to L square. So graph between them would be a straight line, right? So it is option B. Okay, this one is clear. Right, good. Let's see next one. The following four wires are made of same material. Okay, which of these will have largest extension when the same tension is applied? Okay, so when you pull them by same weight, which one will have largest extension? This is the question. Sorry. So now you know extension is equal to what? FL divided by AY. So force is equal, Young's modulus is equal because they are made up of same material. So extension would be proportional to, directly proportional to length, inversely proportional to area. Extension is directly proportional to length and inversely proportional to area. So now we need to find out in which of these length by area is largest. Okay, so that's it, there is nothing else in the question. So if length upon area ratio is largest, that means in that case the wire will have largest extension, right? So let's do that. Okay, right. So length is 200, area of cross section is, everything is given in the same units. Yeah, in the same units. Okay, so diameter is 2 millimeters, so you have 2 square in the denominator. So this is 200 divided by 2 square means 4. So 200 divided by 4 means 50. Option B is 300 divided by 3 square. So 300 divided by 3 square is 9. So 300 divided by 9 means 100 divided by 3. So 33.3. Right. Option C is 50 divided by diameter is 0.5. So let's take 5 into 10 raised to minus 1 square. So this is 25 multiplied by 10 raised to 2. Oh, sorry, minus 2. That goes to the numerator, becomes 10 raised to plus 2. So 50 divided by 25 is 2. 2 times 10 raised to 2 means 100. Option D is 100 divided by 1 square. So that is very good. So this is also 100. Right? This is 50 divided by 25, comes out to be 2. Oh, this was 200, no? Not 100. 200. Okay, so it is option C. Very simple, right? Yes, everyone. Okay, good. Let's see next one. If the ratio of diameters, lengths and Young's modulus of steel and copper wires shown in the figure are P, Q and S respectively. So these are ratios of diameter, lengths and Young's modulus. Ratio of diameters. So diameter of steel divided by diameter of copper. Okay. What is this thing? This is P. Then Young's modulus of steel divided by Young's modulus of copper is Q. Right, Young's modulus of steel divided by Young's modulus of copper. Okay, and no, diameters, length and Young's modulus. Okay, so this is not Q. The ratio of lengths is Q, right? Q is the ratio of lengths. So this is R. No, there is no R. PQS. Okay, PQS. So what is Q? Q is ratio of lengths. Length of steel wire to length of copper wire. Okay. Then the corresponding ratio of increase in their lengths would be, okay, what would be the ratio of increase in their length? So length of steel divided by length of copper. What's that? So we know now that length, increment in length is FL upon AY. So force applied to steel, okay, FL upon AY times length of steel, area of steel and Young's modulus of steel. Then we need to divide by FL upon AY. So that is multiplied by its reciprocal. So that is AY upon FL. But this is for copper, 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 right? Okay. So there is nothing in this question, right? So area is directly proportional to diameter square. Okay, area is directly proportional to diameter square. Okay, so what do we have? Force applied to steel. What's that? So this is 2m and this is 5m. So total 7m times G, that much of force is applied to steel, right? Force applied to copper. Okay, force applied to steel divided by force applied to copper. This is 7m divided by 5m, right? So 7 by 5, that's 7 by 5. So let's do that here itself. This thing is 7 is to 5, right? 7 is to 5. So 7 by 5, because total weight applied to steel is 7m, okay, and total weight applied to there is only one weight applied to copper, that is 5m. So it is 7 by 5. Okay, then length of steel divided by length of copper. Let's arrange this, length of steel upon length of copper. Okay, so this is our P. no, this is our Q. Then you have area of steel, that's in denominator, divided by area of copper. Okay, so I am moving this area of copper in the denominator, and Young's modulus of steel, okay, divided by Young's modulus of copper, that is also in denominator, right? So let's put the values. So this is equal to 7 by 5 multiplied by length of steel to copper is Q, and you have 1 upon area of steel to area of copper. So area is directly proportional to diameter square. So that's why it is directly proportional to a diameter of steel square to that of diameter of copper square. So that would be P square. And then you have Young's modulus of steel to the copper, that is S. That should be answer 7 by 5 Q divided by SP square. Okay, 7 by 5 Q divided by SP square. It is option B. Right, this is just calculation. There is nothing in the question. Okay, good. Let's see next one. Two wires of same material have the radius in the ratio 2:1 and length in the ratio 1:2. If same force is applied on them, then the ratio of their change in length will be. So this is also similar question. So two wires having the radius in the ratio 2:1 means area is in the ratio A1:A2 is R1 by R2 square, that is 4:1, right? Alright, so we want ratio of the change in length. So delta L1 is to delta L2 is equal to, again, FL divided by AY, right? Change in length is FL upon AY, put suffix 1 1 1 1, and dividing by FL by AY is multiplied by its reciprocal, again put suffix 2 2 2 2 here. Okay, so what do we get? So lengths are in the ratio of 1:2. L1 by L2 is 1:2. Okay, so let's cancel out that. So this thing by this thing is 1:2. Let's write 1 by 2. Okay, then radius in the ratio of 2:1. So radius in the ratio of 2:1 means A2 by A1 would be what? It would be 1:4, because A1 by A2 is in the ratio of that is 4:1. So A2 by A1 is 1:4. Okay, so 1:4. What else is there? Same force is applied, so force gets cancelled out. That's good. Then the ratio of their change in length will be, and material is also same, so Young's modulus is also cancelled, right? So it's 1:8. So that's the answer. Okay, option D. Right, this is very simple. Okay, it is clear, Indusha? Okay, let's see next one. The Young's modulus of the material of wire of length L and radius R is Y. If the length is reduced to L by 2 and radius R by 2, the Young's modulus will be, sorry, the Young's modulus of material of wire of length L and radius is Y Newton per meter square. If length is reduced to L by 2 and radius to R by 2, the Young's modulus will be, tell me. It's option B, everyone. Okay, the modulus of elasticity of a material is a constant. It does not depend on its length, area of cross section, etc. It is a constant, right? Okay, good. So Young's modulus is the constant. Good. Let's see next one. When the block of mass m is suspended by a long wire of length L, the length of the wire becomes L plus small l. The elastic potential energy stored in the extended wire is. This is from NEET 2019. Tell me the answer. Elastic potential energy. This is a very simple question, straightforward question. U is equal to half of load multiplied by extension. Right, so half of mg multiplied by what is the extension? Extension is L. That's the answer. Sometimes they ask these very simple questions. Okay, direct formula based question. This is clear? Okay, good. All right, let's see next one. Wires A and B made of the same material. A has twice the diameter and thrice the length of B. If the elastic limits are not reached, when each is stretched by the same tension, the ratio of energy stored in A to that of B is. Okay. So wires A and B made from the same material. Okay. A has twice the diameter and three times the length of B. If the elastic limits are not reached, then when each is stretched by the same tension, the ratio of energy stored in A to that of B is. Okay, so once again, what is energy stored? It is half of load multiplied by extension. Okay, so F times delta L. And what's given? F is same in both of them. So energy stored would be directly proportional to delta L, right? And you have delta L. Okay, let's say delta L is equal to what? FL upon AY, right? So that is equal to, okay, force and area is same in both cases, right? Force and area is same. So it is just directly proportional to length, inversely proportional to area. So what I can say is U1 is to U2 just equal to what? Delta L1 is to delta L2, right? Because they are stretched by the same tension, same force. Okay. And then you have delta L1 is equal to what? F times L1 upon A1 Y1, but force and Young's modulus is same because they are made up of the same material, they are stretched by the same tension. Okay, so therefore it is just equal to L1 by A1 and dividing by L2 by A2 would be multiplied by its reciprocal, would be just same as multiplied by its reciprocal, that is A2 divided by L2. Then just put the values. What is L1 is to L2? A has twice the diameter and 3 times the length. So L1 is to L2, it is 3, right? L1 is to L2 is 3, and diameter of first one is thrice. Okay, so this is d2 by d1 square because area is directly proportional to what? Diameter square. So this is 3 is to 1, right? So L1 by L2, this is equal to L1 by L2 is 3 is to 1, and diameter of first one is 3 times that of the second. So this is 3 is to 1, right? 1 is to 3 square. This thing gets cancelled out and what remains is 1 is to 3. Oh, diameter is twice, sorry, I said. All right. So length of sorry. So ratio of lengths is what? 3 is to 1. Ratio of diameters is 1 is to 2. Right. A has twice the diameter. So this is A2 by A1. Okay, would be D2 by D1 square, and D2 by D1 is 1 is to 2 because first one has twice the diameter. So this is 1 is to 2 square. So that means this thing is 3 is to 4. Right, u1 by u2 is equal to 3 is to 4. So it is option B. Okay, this one is clear. So actually they have asked what is change in length only, what is the ratio of change in length in different way. Okay, what is the ratio of energy stored? Young's modulus of the material of wire is Y. On pulling the wire by a force F, the increase in length is X. The potential energy of the stretched wire is. This is a direct question, right? Tell me. What is elastic potential energy? Half of load into extension, half of force multiplied by change in length, right? So it is option A only, half of F times X. Okay, good, very straightforward question. There is nothing in this one. Let's see next. Two wires of same material and same diameter have lengths in the ratio of 2 is to 5. They are stretched by same force. The ratio of work done in stretching them, same material, same diameter. Okay. Then the work done in stretching them. So what would be the work done? Work done is equal to what? Half of load into extension. Force times extension, delta L. Okay, force is same. That means W1 by W2 is just equal to what? Delta L1 is to delta L2. That's it. Again, this is similar to one of the questions that we saw. Okay. And what is delta L? Delta L is FL upon AY. And out of this, what is constant? What is same? Same material, same diameter. Okay. Same material, same diameter means Y same, A same, they are stretched by same force, everything is same. Okay, just that means delta L is just directly proportional to L, right? Delta L is directly proportional to L. Just put that here. So this is just equal to L1 by L2. Okay, and that is 2 is to 5. So work done in stretching them is in the ratio of 2 is to 5. It's option B. Okay, this one is clear. Right, good. Let's see next one. There is no change in the volume of a wire due to the change in its length on stretching. So volume remains constant. This is given. The Poisson's ratio of the material of wire is. What is the Poisson's ratio? Now this is a good question. Tell me, what is Poisson's ratio first of all? Lateral strain divided by longitudinal strain. So change in diameter. So minus delta D by D divided by change in length. Okay, change in diameter per unit original diameter divided by change in length per unit original length. Alright, so if volume does not change, V is constant, means area times length is constant. Okay, area times length is constant. Okay, so we can say V is equal to area times length, and this is constant, right? Now you want change in length per unit original length. So I can say that change in volume per unit original volume is just equal to change in area per unit original area plus change in length per unit original length. Okay, so from our first chapter, that if y is equal to what? or z is equal to x times y, then what will be change in z per unit original z? So delta z by z will be just equal to delta x by x plus delta y by y. Okay? Yes, no? Right. Then what is area? So area is equal to pi r square, or let's take it's directly proportional to diameter square. Okay, pi d square divided by 4. So therefore this thing can be written as change in A, delta A by A is equal to 2 times of delta d by d, right? That is equal to, see what I have done is, we know that area is proportional to diameter square, not equal to, proportional to diameter square, and therefore change in area per unit original area is equal to 2 times of change in diameter per unit original diameter. We can put that over here. Okay, so 2 times, this is 2 times of change in diameter delta d per unit original diameter. Okay, plus you have delta L divided by L, and now what I can say is, because the volume is constant, this thing, the change in volume per unit original volume is equal to 0. So this thing is 0, right? And therefore what I can say is minus 2 times of delta d by d is equal to delta L by L, or I can take the 2 on that side. Okay, so minus delta d by d is half of delta L by L, or if I take ratio of minus delta d by d to that of delta L by L, what do I get? I get half. Okay, so you can substitute that here and you will get Poisson's ratio is equal to half. Okay, so that is 0.5. So this thing is clear? Yes, no? Right. So now here we need to be careful about the sign also, because see, minus half is also there, minus 0.5 is also there. Okay. All right. So I think this was good question. Otherwise all questions are direct formula based or comparison based. Okay. Even comparison based is good. Anyways, let's see next one. A metal rod is fixed rigidly at two ends so as to prevent its thermal expansion. Okay, metal rod, it is fixed at two ends to prevent its thermal expansion. If L, alpha and Y respectively denote the length of the rod, coefficient of linear thermal expansion and Young's modulus of its material, then for an increase in temperature of the rod by delta T, the longitudinal stress developed in the rod is, tell me. So thermal stress, just remember the formula, thermal stress. Somebody told the answer, it's equal to Y times thermal strain, and thermal strain is just alpha delta T. And now check your options. Inversely proportional to alpha, it's not inversely proportional to alpha. Inversely proportional to Y, no. Directly proportional to delta T by Y, no, right? It's directly proportional to delta T but not inversely proportional to Y. This is also not correct. That means this should be correct. Okay. Independent of L. So there is no length in this formula. That means thermal stress is independent of length. Okay. Again, simple question. Right. Good. Let's see next one. Two rods of different materials with coefficients of linear thermal expansion alpha 1 and alpha 2 and Young's moduli y1 and y2 respectively are fixed between two rigid walls. Okay, so two rods, different materials, different coefficients of thermal expansion and different Young's moduli. They are fixed between two rigid walls. They are heated to have same extension, sorry, they are heated to have same increase in the temperature. If rods do not bend and alpha 1 is to alpha 2 is 2 is to 3, then the thermal stresses developed in the two rods will be equal. So you want thermal stress to be equal when y1 is to y2 is equal to. Okay, so the increment in temperature is also equal and you want thermal stress to be equal. So thermal stress in one, or let's call stress as what, sigma 1 is to sigma thermal. Okay, sigma th1 is equal to sigma th2, right? So what is thermal stress? That is just equal to y times alpha delta t. So y times alpha delta t of first one should be y times alpha delta t of the second one. So delta t is equal, and this is y1 alpha 1, this is y2 alpha 2, right, for first and second material. Delta t is equal, so we can cancel it out. So y1 alpha 1 is equal to y2 alpha 2, and therefore now you want ratio of y1 is to y2, so that would be equal to alpha 2 is to alpha 1, right? So this is alpha 1 is to alpha 2 is 2 is to 3, that means this is equal to what, 3 is to 2. So that's the answer. Okay, very simple, right? This is simple. Yes, no? Okay, good. All right, so that's the end of questions based upon properties of solids. Okay.